Okay, so let's get started with the fourth day of the course. Yesterday we covered basically how to avoid overfitting using the bruising Kerner spaces. We talked a little bit about what overfitting means. I think I mentioned the first day that the word overfitting might be a little bit misleading because it's not really, so the problem is not really that the rule fits perfectly the training samples. The problem is that what happens with the training samples might be very different to what happens with the samples at prediction. So fitting training samples very well is not really a problem, and there are multiple methods that fit the samples, the training samples perfectly. Okay, anyway, so we saw yesterday that the reproducing Kerner spaces can avoid those problems basically by controlling the size of the norm of the functions in the reproducing Kerner space. So then at the end of yesterday, based on those arguments, the idea is to use empirical risk minimization, in which we bound the norm of the functions, and we also said that constraining the norm of the function is equivalent to have a regularization parameter. So I'm going to directly write it in the usual way. We have a loss, and we try to minimize the loss for the training examples. And also we want to have a small norm of the function, right? So this is the type of problem that we want to solve, and as we said yesterday, so this is a good idea in terms of overfitting and so on, but it seems very complicated to solve because the variables here will be functions in some Hilbert space, and that's very complicated, right? So today we are going to describe two ways to address these problems. First is going to be the traditional way to do it. And the second one is going to be a little bit more modern. I also want to mention that how to address this type of optimization problems efficiently is very active research topic. Multiple people are trying to improve these things because it's believed that the main limitation of these methods is the fact that doing this efficiently is hard. Okay, so let's do the classical way to do this optimization. So it's basically based on something people call representer theorem. Okay, so the representer theorem in this for this type of techniques says that, let's call this optimization problem P. So it says that there is a solution of P of the form f of x equal to the sum alpha I q x out x. Okay, so basically at least one solution of the optimization problem is of this very simple form, and we could have something stronger in the usual case, and in addition, if lambda is strictly bigger than 0, I mean, we didn't say yesterday, but we could also put the regularization to 0. But if the regularization parameter is strictly bigger than 0, all the solutions, of that. Okay, so like think in the second day and also in the first day, but maybe with not matrix notation, we saw that in the finite dimensional case, all the functions are combinations of sections, and in the general case, combinations of sections give us dense subset of functions. Right? So, and we also said that the one way to think of the functions in a reproducing kernel Hilbert space is a combinations of sections. And this result says that the solutions of this optimization are combinations of sections, and not only that, are combinations of sections of the training samples. Okay, so the xi's here are the specific x's that we have at training, and the number of terms of this sum is equal to the number of training samples that we have. Okay? So this theorem basically says that the solutions of this optimization problem has a very simple form. So let's prove that. Let's prove that. Okay, let's start here and then maybe finish there, or maybe we can in this side. The proof is quite simple. Okay, so to do the proof, maybe first I'm going to recall a result of Hilbert spaces. This is something that we can call the projection theorem. I mentioned the other day with Xavi this theorem, but I think it's good if we refresh this. So basically, if we have a Hilbert space and we have a linear subspace that is closed, linear subspace and closed, then we can write the Hilbert space as the direct sum between M and the orthogonal subset. And then let me see if I explain what is it. So this means that each element in F can be written in a unique in only one way, as the sum of an element in M as an element in M orthogonal, and M orthogonal means the elements in H that are orthogonal to all the elements in M. So this is, I guess, familiar to all of you, but just to recall, this is a compact way to say it. So this result is very familiar in the usual linear algebra, right? In the finite dimensional case, is like, of course, I mean, you can always do this. In general Hilbert spaces, you need that the subspace is closed. And what else? Yeah, so we have this, and also, I don't think that we are going to use this, but basically, the orthogonal or the orthogonal recovers the original subset. Okay, so this is just a useful result for these things. Okay, so let's do the proof. Okay, so to do the proof, I'm going to call M the set of functions that is like this. So these are going to be functions in H such that F is the linear combination of the sections of the x's in the training samples. Yeah, maybe I should. and x1 to xn are the instances at training. Okay, so M is the set of functions in the Hilbert space that are linear combinations of sections of the training examples. This subset of H is clearly a linear subspace. We can do combinations of these type of functions, and we will have another functions of the same type, and we can multiply by constant, right? So this is clearly a subspace. The fact that this closed is a consequence of the fact that this is a finite dimensional subspace, right? So the dimension of this subspace is at most n, right? Because it's just linear combinations of n specific functions. So this is finite dimensional. So every subspace of finite dimensions is closed. Okay, so then we can use the projection theorem, and then we will have that we can decompose the functions in H as one function in M and one function in the orthogonal of M. And that's basically what we are going to use to prove the result. So to actually prove the result, we can, so simple way to do it is let's assume we have a function and we have a solution of the optimization problem, and let's assume that that function is not in M, right? So basically the result is trying to show that at least there is one solution of the optimization that is in M, and in the case that the lambda is strictly bigger than 0, we are going to prove that all the solutions have to be in M. So we can do it by contradiction. So basically, let's see what would happen if F star is a solution of the optimization problem, and F star is not in M, right? So since M is a subspace that is closed, we can always write F star as F1 plus F2 with M1 in M and F2 in the orthogonal. And since we are assuming that F star is not in M, we have that F2 has to be different to 0, right? Because we are assuming that F star is not in M, so F2 has to be different 0. And then let's continue here. Okay, so we have the solution decomposed as the sum of one function in M, one function in M star, and if 2 is not 0, right? So I guess you might see what I'm trying to do. So basically what I'm going to show is that the value of the objective function in F1 is going to be smaller than that in F star. So if we prove that, right? So if we prove that the value of the objective function in F1 is smaller than that in F star, we are done, right? Because then F star could not be a solution of F of B. Okay. So let's prove that. So if I evaluate the objective function in F1, if I evaluate the objective function in F1, it's going to be something like this. Now, we can use the reproducing property, right? So both F and F1, I mean, all the functions here live in the reproducing Kerner Hilbert space, so that this F1 evaluated in X1 is the inner product between F1 and the section. And if instead of F1, we would have F star, where should I write it? Here. The value of F star at xi is going to be the inner product of F star with the section. And since F star is F1 plus F2, this is F1 plus F2 inner product with the section, right? But now F2 is in the orthogonal of M. So when we do the inner product of the F2 with the section, we get 0, right? So F2 is orthogonal to all the elements of F, and the elements of F are linear combinations like this. So in particular, each of these sections are in M. So when we do the inner product of this and this, we get 0. So basically, these two things are the same. Yeah. Exactly the same. Right? Okay, I am running a little bit out of space, but I'm going to remove this later, so we should be fine. So this, the objective function evaluated in F1 is exactly the same. The first part is exactly the same if we do it with F1 or if we do it with F star, because of this, and then we have the norm of F1. Okay. Move this. And we are basically done, right? Because F star is F1 plus F2. And F1 and F2 are orthogonal because F1 is in M and F2 is in M orthogonal, so that the square norm of F star is the square norm of F1 plus the square norm of F2. Right. So this quantity here is going to be always smaller or equal than 1n, than the objective function in F star. This is I, no, F star, sorry. Star. Okay, just because of this, right? So the norm of F1 is always going to be smaller than the norm of F. Indeed, the norm of F1 is going to be strictly smaller than the norm of F2 because F2 is not 0. Right. Let me be more specific. Because we have this equality and this is not 0. So then in here, this quantity is smaller or equal than this other quantity. The only way that these two things can be equal is if lambda is 0. That's why we have two cases, right? So in general, the value at F1 is going to be smaller or equal than the value of at F star. So that if F star is a solution, F1 is also going to be a solution, so that we have the first part of the result. If we have a solution, we can always find a solution of this form. If we have a solution F star, we can always find a solution that is linear combination of this. And if lambda is strictly bigger than 0, this inequality is strict. If lambda is bigger than 0, and then it's not possible to have a solution that is not in M, because for every function that is not in M, we can find a function in M that has a strictly smaller value. Okay, so proof is quite simple. Okay, and we again use the same type of properties as we always do, reproducing properties and simple properties of Hilbert spaces like the projection theorem. What else? In some books or something, you might find this result in a slightly more generality. So in books, you can find this result as the regularization term can be some function of the norm of f with f increased. I mean, the way we do regularization does not need to be always like this. We can do some other type of regularization with some other function that is increasing in terms of the norm. As you can very easily see, the proof would be basically the same thing, right? Because in here we are just using that this is strictly smaller than this. So if instead of multiplying by lambda, you do some other increasing function, the result will be exactly this. But in practice, almost always you do this type of regularization. Okay, so this is the representative theorem.
Sure. How do you ensure that the problem has solution?
Yeah, this is a good question. Okay, so well, I didn't explain what type of loss function we are going to use, right? So yesterday I said that a little bit like 0-1 loss might be natural for classification and so on, but it's not something that you might want to use in practice, right? So in practice, you want to use a loss function like the second one I put yesterday, like this logistic loss. So you need so you want to use a loss function that is continuous, at least continuous. If it's convex, it's better. So usually you like to, at least for this type of techniques, you will always use convex and continuous function. And this optimization then is optimization over a compact set, and with this type of arguments you can find. So this is one way to say it. Other way to see that this has solution might be also like a consequence of this result, right? So I mean, this optimization problem is in a difficult space, Hilbert and so on, but this proof we are basically showing that for every element in here, we can always find another function in this finite dimensional space that has a value that is smaller or equal, right? So basically, we are saying that this optimization problem, either with min or with inf, is equivalent to an optimization problem in this finite dimensional subspace, and then you can use more simple arguments. So yeah, okay. So of course you would like to do this not with the 0-1 loss, but with logistic loss or some other losses like hinge loss or something like this. Yeah, since we are talking about that, for instance, if you use a loss called hinge loss, this method is called support vector machine, and or kernel support vector machine. Okay. So this result then enables to to have a more tractable optimization. Basically, if the solutions of the optimization problem are of this simple form, we can just search over functions of this form. Right? So the optimization problem there is going to be equivalent to optimization problem now in the alphas. Right? So now the variables that we are going to have are just going to be the alphas, just in real numbers instead of a function. And yeah, let's write it down. How the optimization problem will be. So it will be the loss, and then f of at xi is going to be okay. Let me change the notation. Well, I guess you know what I mean. So it's going to be the sum over j of alpha j evaluated in xi xj yi. So the functions are combinations of the sections. In here I was using I for both things, but now I'm going to use j for this combination and I for the sum over here. Right. So the value of those functions at one xi is this linear combination. And so that's for the part of the loss, and then for the norm, we know how to compute the norms of the elements that are combinations of sections, right? So those norms are the easy ones to compute, and we know that that's just doing the usual inner product. Yeah. Right. When we have used multiple times. So basically the optimization problem there is equivalent to this optimization problem. Now the variables are n real numbers. So this is a usual optimization problem. And basically in here, we can see that something that I also mentioned the first day, right? That these ideas of the kernel trick, that as long as we know how to compute the kernel, that's pretty much enough, right? So in here, the only thing that we need to use are the values of the kernel at the different pairs of xi, xj, right? So even if the x's are something that are not maybe vectors, they are maybe, I don't know, graph or whatever, as long as you have a way to compute the kernel, as long as you have a way to describe the similarity between pairs of x's, you can use this type of techniques. Okay, so this is the optimization problem that you solve at learning, and then just for completeness, after you solve this optimization problem, so this will be what your fit function will do, solving this optimization problem, and your predict function for one specific x will do the sign of this type of functions, but now the functions are like this, so it will use let me see how to write it. It will use the solutions of this problem. So the alphas would be the parameters of your classifier, the solutions of this optimization problem, and then it will compute the value of the function at that specific x, and then check the sign of that function. And so this is just direct consequences of what we were doing. As I said before, And both for the training and for the prediction, you don't really need to, it's enough for you to be able to compute the values of the kernel. You don't need to work in feature space or anything like this. Okay, so that's okay. So this is one way to actually do it in practice. Well, I didn't say how to solve this optimization, but this is you can use any conventional solver of linear convex optimization. Yeah.
Can we be like a thing in supervector machines also an interpretation to the alpha coefficient?
So if the loss is like a hinge loss, sometimes what happens is that most of the alphas in the solution. So usually what happens is that I don't know if most, but at least multiple of the alphas are zero. And then the alphas that are not zero, people call it support. Support. So basically in here we have one parameter for each training sample. So in support vector machines, some of the alphas are zero, and so that only some training samples matter at the end. And people call those support points. But yeah, in other techniques, most all the alphas, I mean, it depends, right? So if you use other type of regularization, maybe you also get the parameters to be zero. So it depends on the technique. Also, even in support vector machines, the proportion of alphas that are zero is not so high, so fine, but also not that great. Okay, so this is like the traditional way of using reducing kernel hidden spaces in supervised learning. Basically, you would solve this optimization at training, and then at prediction you will compute this. And yeah, and this is nice and tractable. Yeah.
So the theorem yesterday that showed that the overfitting went down as a square root of n, like root full. But now it seems here that actually the solution grows with n as well.
The solution, the number of parameters.
Yes.
So well, I mean, so basically in here, I mean, the number of parameters, yes, in this video, and we will be talking about that because that's the problem with this.
Yeah, right. So basically the complexity of the solution grows with the number of training samples that you have.
Well, but so basically, you have to make the model more simple, if you like, basically by. So the way you make the model more simple is increase this regularization parameter, which is the same as considering functions with a smaller norm, right? So if you pick a larger lambda, the number of variables will be the same, still n, but you want this part describing the norm to be as small as possible. So most of the variables will be very near zero. And if you use techniques that try to find sparse solutions, you will have more and more coefficients that are zero. So basically, you will penalize this norm here, and so then the variables will be smaller and smaller. But yeah, the number of variables is n, and that's the big problem of it. But basically, the way you control the complexity of the model is by tuning the regularization parameter. The number of parameters, if you use something like hinge loss, you might get some alphas to be exactly zero, but not that many in any case. Okay. Okay, very good. So this is the way that the people use this for a long time.
Can I ask?
Sure.
So shouldn't the theorem from yesterday depend on the maximum value that these parameters lambda alpha can take?
Well, I mean, so yesterday was So everything was related to the norm of the function, right? So the norm, so the norm of f, well, it's basically there, right? So the norm of f is going to be, for this specific f's, the norm is basically that thing I wrote there, right? So making this norm small
Okay.
is basically picking alphas that are small, right? How these two things are related depends also on what kind of kernel you are using and that sort of thing. Okay, great. So good. Yeah. So as I was saying, this is the way that these things were implemented for a long time. But as you was mentioning before here, a problem is that this, I mean, this is better than what we had, much better than what we had before, because before we had an optimization problem over infinite variables. Now here, at least the number of variables is finite, right? And this is more tractable, but still, this will be too hard when n is large, right? So if n is large, let's I don't know, 1 million, right? So if n is 1 million, solving an optimization problem with 1 million variables, it will take forever. So this will be too complex. Right. So if we have many training samples, solving this optimization problem will take forever. Right. And in the past, that forced people to use this type of techniques only in cases with a limited number of training samples. Yeah. Okay. So now we are going to see a way to address this type of optimization problems that alleviate these type of problems. There are many ways, and as I said before, this is very active topic of research, but we are going to just do something simple. So, yeah, let's start with this. Okay, so the one way to make it more efficient when you have many training samples is like going back to the feature map representation, right? So the first day I was saying that working with reproducing Kerner Hilbert spaces can be interpreted as working in a feature space in which the rules are just linear rules, but in feature space, right? And the first day I saw that that might be problematic because the feature space can be very high dimensional or even infinite dimensional, right? And then the kernel, using the kernel trick was a good idea because then if you use the kernel, you don't need to work in feature space anymore. You don't even need to know what the feature is, and okay, and this sort of thing, right? So that's good for certain things, but it also has these limitations, right? So now we are going to see how to address this problem working in feature space. But we are going to work in a slightly different feature space to make it possible, right? So if, for instance, if we were working in a feature space that is finite dimensional, like if this reproducing Kerner space will be a polynomial, even by a polynomial kernel, right? Then we could represent the functions as linear combinations of monomials, right? As we were discussing, so we could actually work in Hilbert in the feature space and represent functions as inner products between our the feature representation and some parameters, right? And this the size of this was RD, and D was
the dimensionality of feature space, right? So these are the things that we were discussing the first days. For instance, if the kernel would be the polynomial kernel, we can actually do this, and capital D will be a finite number, right? We said that might be very large, but we could also work this way, and then we could, the optimization at training could be an optimization over mu's, right? Over vector of size RD, and then we will have the loss depending on the mu. And then for the norm, at least if the representation in terms of in feature space is unique, we could also penalize the same way, right? We saw that the norm in the Hilbert space is the same as the norm in feature space, at least in the cases where the mu is unique, right? So we could work in feature space and solve these optimization problems. The problem of these cases is that the D might be large now, and then we are in same type of problem, right? So for instance, if we were using like a polynomial kernel of degree 2 or something like this, right? We could choose to solve the problem using the kernel, or we could choose to solve it using the monomials up to degree 2, right? Both cases, maybe the dimensionality of the optimization would be similar, right? But in general, as we said the first day, this didn't sound like a very good idea, because in general, always D is very large. So this D is not really dependent. This D does not depend on the number of training samples that you have. It just depends on how rich is your feature space. Okay, so this didn't look like a good idea. So people use this approach, and then like 14 years ago or something like that, people realized that this can be done, but doing things approximately. So that's what we are going to do now. So basically the idea is that we are going to work in feature space, but not exactly the feature space corresponding to the kernel. We are going to use approximate features, and indeed the features are going to be random features. Okay. Okay, so yeah, let's do the how to address this optimization problem, but now we are going to do it with random features. So there are these type of features. People have developed these type of features for many different type of kernels, and we are going to do it for the kernels that are shift invariant. We also talked about those on the second day. Right, so kernel is shift invariant when there is a function such that the kernel is that function only depends on the difference between the 2 points. And then I describe a theorem that is Kerner theorem, saying that if we are in this situation, there exists a function such that this phi representing the kernel is given by the exponential of I. I believe the day I wrote it, I did it for the dimension 1, but it is exactly the same in general. So if X lives in RD, the result will be like this, and basically we will be doing a Fourier transform in higher dimensions. Okay, so thanks to this result, we know that this function can be written this way for I said the other day, a positive measure. Yeah. So for now, we are going to assume that function at 0 is 1. That is something that we can always get just by normalizing if necessary. So if this function is 1, then this measure is a probability measure. These are also some of those type of properties in Fourier analysis that if you have the function in the time domain is 0, then the Fourier transform and the integral is 1, and that sort of thing. Basically, if this function is 1 at 0, it means the integral of this is 1, which, well, is straightforward from this equation, right? If we put in here 0, the exponential disappears, and then, right? Okay, so basically, if we normalize the kernel corresponds to a probability distribution this way, right? And that's basically Buchner's theorem. So in that case, then we have the following simple result. So in that case, then we have that the value of the kernel at 2 points is going to be the expectation over that probability distribution of the cosine of W x1, product between W and x1, and the sine of W transpose x1, and then cosine W transpose x2, and the sine W transpose x. Okay, so basically, if we are in a situation like this, the kernel is given by the expectation of these products between sines and cosines. So it's cosine times cosine plus sine times sine. And so before we do the proof here, I should put an example before, right? So 2 days ago, we were seeing this type of kernels when we discussed the Gaussian kernel, right? So for the Gaussian kernel, the corresponding function defining the kernel was let me see. Oh, yeah. Firstly, the exponential of -1/2, and then the norm square sigma square. I believe 2 days ago I did it with x squared because I was doing the one-dimensional case, but okay. So the Gaussian kernel corresponds to this function, and then this function is the integral of exponential in here. Okay, let's do it like this: 2 pi d divided by 2 and 1 divided sigma square to the d half of the exponential minus if I am no, sorry, this the sigma is multiplying and it's a constant. Okay, so yeah, so basically in the Gaussian case, the probability distribution corresponding to the Gaussian kernel is a Gaussian distribution. So the PW corresponding to the Gaussian kernel is a Gaussian distribution with zero mean and covariance 1 sigma square times the identity. The fact that these two things are the same is one of the usual examples in a Fourier transform. So basically, the Fourier transform of a Gaussian is another Gaussian, and basically the standard deviation in here the standard deviation is sigma, and in here the standard deviation is sigma. Okay, so basically for the Gaussian kernel, the corresponding probability measure is a Gaussian measure, and the variance is given by the inverse of the scaling parameter. Okay, so this is an example. As I mentioned a couple of days ago, multiple kernels can be written this way, and for each kernel that can be written this way, you will have the corresponding probability measure, and that will be some distribution, and you will also have this result. This result is general, not only for Gaussian, but for any kernel that can be written like this. Okay, great. So let's prove the result and then see how that can be used. The proof is straightforward, but let's do it. So, so the kernel is a real number, right? I think I mentioned also 2 days ago that everything can be done also with complex value functions and so on, but at least for machine learning, it's more useful to think in terms of real functions.
So just a quick question. So omega multidimensional?
Yeah. In here I'm doing it for the multidimensional case.
Okay. It's of the same size, the measure is of the same
Right.
of the offense.
Right.
Okay.
Yes. 2 days ago, when we talk about Gaussian kernel, I mostly talk about the one-dimensional case to talk about frequencies and so on in a more simple way, right? But things can be done in a multidimensional case, and in practice, what you are interested is in the multidimensional case, right? Okay, so the kernels are a real number. The value of the kernels is a real number, right? And since this is x1 minus x2, right? That's what happened with our thing, right? Phi in x1 minus x2 is the exponential of this thing, but since the value is a real number, we can as well take the real part. Let's do it. So it will be the exponential of I x transpose w, and then the w. Okay. So the real part. Okay, sorry. Here is x1 minus x2, transpose. Yeah, you can see it, right? So it's the exponential of I times x1 minus x2 transpose w. 1 minus x2. Okay, so then we keep going. So the real part of the exponential is going to be a cosine of x1 minus x2 transpose w, dw. And well, now one of these qualities that people learn at some time about the cosine of the difference. So the cosine of the difference is cosine times cosine plus sine times sine. Okay, so and then in addition to do that, I'm going to change the integral notation with expectation notation, right? So If this is a probability measure, the integral is the expectation with respect to the distribution, and then we have cosine of x1, cosine of x2, cosine of x1 times w, cosine of x2 times w, plus sine x1 w sine x2 w. This is just of the elementary properties of sines and cosines. Right, so the cosine of the difference is cosine times cosine plus sine times sine, and that's the result we are trying. It's kind of simple, but nice. Okay, so this is the result. Should we go for a coffee or no? Okay, let's finish this, and then after the coffee we start a different topic. Okay, so now since we have this result and we can write the kernel as the expectation of a product of a bunch of sines and cosine, something that we can do is to define feature mapping, right? So the kernel is going to be the expectation of these sines and cosines, right? And the W's are going to follow this distribution. So before I was saying that using the actual feature mapping might be too complicated, but doing something approximate and something random is going to be a good idea. So if we have that this is the expectation of that, something should be kind of natural so if we want to do something approximate random, I guess it should be to think of computing this expectation using random sampling or using Monte Carlo integration, depending on how you think it, right? So the true kernel is exactly this expectation. We can approximate expectations just by doing getting random samples, right? So we can get n random samples following this distribution and approximate the actual kernel with a scalar product of all these values. Right? Yeah, okay, let me do it in more detail. I just wanted to give the idea, right? So the idea is, if the kernel is exactly like this, instead of doing the expectation exactly, we are going to do it approximately using random samples. Okay, so random features will be as follows. So first of all, I take n IID sample from that distribution PW, right? So depending on the kernel that you use, you might do the random samples following a different distribution. For instance, if the kernel that you want to use is the Gaussian, you will get n random samples of a Gaussian with zero mean and covariance given by the index of the scaling parameter. So you will get these n random samples, and then you can define an approximate feature mapping that is going to take the x's into, so if I want to get that, the feature mapping is going to transform the x's into vector. Should I do it in column? Yeah, let's do it in column. So the vector is going to be cosine W transpose x and sine W one transpose x. Cosine W n transpose x sine W n. Right. So So the feature mapping is going to transform the X into this vector. Right? So the examples of feature mapping I was discussing the first day was polynomials and this sort of thing, but this is a perfectly valid type of feature mapping, and it's also reasonable type of feature mapping, right? So in here, basically, we will be considering functions that are combinations of sines and cosines, and this will be a vector in R to the 2n. So we can control how big is the dimensionality in this feature space by controlling how many random samples we get. Right? So if we do this feature mapping, now the kernel corresponding to this feature mapping, would be just as we always did, right? So the kernel, the feature space here is just usual vector. So the kernel, let's do it. So the kernel corresponding to that feature mapping will be just doing the inner product of the vectors, and then if we do the inner product of these two vectors, we get. Should I write it? No, I think I'm not. Well, okay, let's write. So it's going to be 1 over n, and then we are going to have the sum. The sum 1, 2, n of that quantity. So we will have cosine x1 w I cosine. We have also the sine. Yeah, putting the transport at the end of the thing. Okay. So now, if we have this feature map and we do the inner product of this with the same one with x2, we will have that expression there, which will give us an approximation to the kernel that we are really interested in. So if we do this, if we use this feature mapping, we will end up working with a kernel that is not the one that we might be interested in, maybe not the Gaussian kernel, but is going to be similar to the Gaussian kernel. And the approximation between these two kernels is going to, the difference between the kernels is going to decrease as we get more and more samples here with the square root of the number of samples and the usual properties of approximating these quantities. Okay, so that's basically the idea of this other way of addressing the optimization problem, is basically actually working on feature space, but in this type of feature space that is not exactly the feature space corresponding to the kernel that we might be interested, but it's going to be a feature space corresponding to a kernel that is similar to the kernel that we are interested. Okay. So this is an approximate.
What are the limitations of doing this? Apart from the thing that you are increasing your expectations, so you need to, like, you have the problem of increasing the number of n. What are there, like, other limitations of this kind of random future method?
The main limitation is that the number of random features that so the number of random features that you need to have a very accurate approximation of the kernel might be high. So that's the main limitation. In practice, is not a big limitation in the sense that
in the sense that it doesn't really matter much if these two kernels are very similar or not. Because usually in practice, the way you choose the kernel is not like, okay, I have to use Gaussian and it has to be exactly the Gaussian and it has to be exactly with a scaling parameter of 0.33, right? So the kernels are usually chosen just because they will give you general functions, right? But so if you use a kernel that is slightly different, it's not necessary that that kernel is going to be worse than the other, right? So, yeah. There are a lot of, there are multiple works that try to describe the error caused by using these random features, not in terms of the approximation of the two kernels, but in terms of the accuracy of the final rule as you increase n. That's more meaningful, but also much more complicated. And here is just basically approximating an expectation, but how the number of random features affect the final performance of the rule is not that easy to do.
So in practice, you can compute that and like by cross validation, or you have like certain properties about this that tell you.
I think so. People that I think for this, yeah. So there is no. I don't think there is a recipe that tell you, okay, you should use 1,000 or 500. People use in the order of 100. So as I said before, this is very active research, quite active research area. So because people have also observed that the more you complicate these things, the performance is better. So sometimes is useful to have a very high dimensional representation. Maybe not with random features. So with random features, I have not seen papers with more than 1,000 random features. I think hundreds is the usual. But using other type of techniques that use a different type of feature representation, yeah, people try to have as many features as possible. So yeah, that's a good question. I don't know. For random features, it seems that with in the order of hundreds is enough to get reasonable performance. With other techniques, it seems that more and more is better. So yeah.
With this, you solve the feature space based.
Right. So with this you will solve. So with this you would actually transform the x's with sines and cosines, and then solve it as if it were a linear rule. Yeah. So with this, you forget about the kernel trick. You transform the x's with this vector, and then you will use it as if these were the original x, and do a linear rule. Yeah. So that's the. Okay, so if there are no more questions, yeah, Nicolas.
No. O sea, it was a question, but not about the.
Okay. Yeah. So so let's stop for a few minutes, take a coffee, and we come back. Okay. So now, if you don't have more questions about the previous topics, we are going to change gears and start a new type of application of reproducing Hilbert spaces for machine learning. That is going to be the last type of topic of the course. So this we can call it a kernel mean embedding. Okay, so this type of techniques have been used in multiple applications of machine learning. We are going to discuss the main ideas, and tomorrow one or two specific applications. Okay, so let's introduce this new idea. So we have been talking that about the one way to introduce the the reproducing Kerner Hilbert spaces is by using a feature map. And that was also the natural way to start thinking about the reproducing Kerner Hilbert spaces, because basically this help us represent each instance by an element in a Hilbert space, right? So the feature mapping is useful because it represents the data that we have as elements in a Hilbert space. So, for instance, we could make a very high dimensional representation in which we can separate the data using just very simple linear rules, etc. Right. So we have been using with this type of representation of the instances. So basically, this mean embedding, what is doing is, instead of is a generalization of the feature mapping, in which we are representing not only specific instances, but we are going to represent probability distributions of instances as elements of the in the feature space. Okay, so basically we are going to extend this representation to be not only for specific instances, but for probability distributions over instances. Okay, so now let's start thinking how to extend the feature mapping to represent not only specific instances, but the probability distributions. So the extension is very natural. It's basically the only reasonable way to do it. So reasonable for it. So this representation is going to be a linear mapping. And yeah, let's talk 1 minute about what I mean with this, right? So the representation is going to be linear, and linear structure of this space is clear because this is a Hilbert space, right? X can be whatever, right? But even for any type of space, the probability distributions, I said it in words specific. With here, I mean the probability distributions or probability measures over X, right? So probability distributions always have a linear structure, in the sense that we can, I mean, more than linear, it will be a affine structure, in the sense that we can always combine probability distributions by doing a convex combination, right? So if you give me two probability distributions, I can combine those two distributions. For instance, I can create the distribution that is a mixture of the two distributions with a weight 1/2, right? Or I can use any other combination, right? So if I have two elements, if I have two probability measures or two probability distributions, I can always do the mixture of them. I can always combine them, and I will achieve another distribution. Doesn't matter what is the support space, right? So that's what I mean, that this always has a affine structure, right? So basically, the plan is to extend this to a function from distributions into feature space in a way that is linear, and it corresponds to, and it's an extension of this. So with this information, there is only one way to do it, but let's maybe do it together. So if I want to extend this representation, I might say what is good. So how is going to correspond to this, right? So if I have one specific element in X, what is the distribution that corresponds to that element? It would be
the distribution that has probability 1 in that specific X, right? So people usually denote that with a delta of X, right? So this is the probability distribution in which the specific element of X, small x, has probability 1 and the rest of elements have 0 probability, right? So if we want to extend the feature mapping with a function here, well, so this will go to the, oops, sorry, no. This will be in a couple of minutes. So for now we are like this, right? So okay, so we want to extend this correspondence now to take probability distributions. If we really want to extend it should do the same thing for, okay? So elements correspond to probability distributions that have probability 1 in that element. So that's how we do it. Now, if we have an actual probability distribution, how this function should be. Okay, let's first do the case with simple probability distribution, right? So let's imagine that now we have a probability distribution given by 2 points, right? And maybe some alpha. So if we have a probability distribution given by 2 points, what should be the transform thing? So this is because I want to extend this, right? And I mentioned that I want to do it in a linear way, right? So this thing should go to, well, doing the same combination, but in terms of this thing, right? If I insist to make it linear, this is the only way to do it. And in terms of probability distribution, right? So if this is a probability distribution, that is, so this probability distribution has probability alpha of b in x1, probability 1 minus alpha of x2. This quantity here, in terms of this as a probability distribution, would be, would be the expectation. So if we see this as a probability distribution, this will be the expectation of the feature map with respect to right? This, right? So if I have a distribution that is like this, x1 has probability alpha, x2 has probability 1 minus alpha. This quantity is just doing the expectation of phi with respect to this, right? And also in this case, right? So this is, if the distribution has probability 1 in only 1x, this is also the expectation. And that's what we can do in general, right? So we can extend the feature map to not only to specific instances, but to probability distributions over instances by taking expectations of the feature map. Right? This is basically the only reasonable way to extend the feature map is probability distributions would be like this. Right? Okay, so this is nice. Okay, let's see what we are doing if we do this. So if we do this type of mapping, right? So this mapping here is representing each specific instance as some vector in a Hilbert space, right? So we were saying before that, for instance, if we use a polynomial kernel, we are representing each specific x by maybe 1 and x and x squared and x cubed and so on, right? So we are representing an instance by an element in this linear space, in this Hilbert space. And here what we are doing is representing probability distributions in this Hilbert space. And that can be useful for many things. I guess
most of you have tried to use probability distributions in multiple ways, and you know that working with probability distributions is often difficult because they can be difficult objects to work with. In here, at least, we are giving them a very nice structure as a Hilbert space, and indeed we are going to give the probability distributions a structure of the reproducing Kerner Hilbert space. So if we do this type of mappings, we transform probability distributions into elements in these nice Hilbert spaces, and then we can work instead of in the space of probability distributions in these nice Hilbert spaces and use all the nice properties of Hilbert spaces and the nice properties of reproducing Kerner Hilbert spaces, inner products, all of the nice properties that we have seen before. Okay, so that's the plan. And there are many applications that can be done this way. Okay, so this is sure.
Just to understand, you're saying that we can, for a given probability distribution and a given mapping, we can study them in the Hilbert space.
Yeah.
And then use that to say derive things on about the actual probability distribution.
Right. So in this can be used for many different things. Tomorrow we are going to see a few applications of this type of ideas. So for instance, now in this Hilbert space we have inner products and everything, so we can define distances between probability distributions. We can do like we can find the probability distribution that is closest to some other distribution using the nice properties here. What else I'm going to say? When we do this transformation, right? So depending on the feature mapping that we choose to use, we are going to encode different properties of the distribution. For instance, if this would be like the polynomial feature mapping, with this transformation, we will be encoding multiple moments of the distribution.
Okay.
Right. So, so maybe depending on the application, we might care about some things or another, and then. Okay, good. So this is like a general kind of idea. These things, in principle, could be done for any feature mapping. And I guess some people use it in more generality, but most of the works use a very specific feature mapping, which is the feature mapping that we call before the canonical feature mapping. So when people talk about the kernel mean embedding, basically the transformation that they have in mind is, or that they use, is to transform the probability distributions into a reproducing kernel Hilbert space, and is the extension of the canonical feature map that we saw before. So the canonical feature map was moving each x into the section corresponding to that x. So the canonical feature map. I don't know if I put notation for this. I don't. The canonical feature map is moving the x's to the Hilbert space. I think we use this in the proof of some of the equivalences, right? And is taking each x into the section of the kernel corresponding to that x, right? All right, so then the extension of that to now transform probability distributions is just the thing I said before, but for this specific feature map. So it would be the expectation over P of the sections, right? So the distributions depends on X. So we will be doing averages of sections, and then the result is going to be another function in the Hilbert space, right? So If we do this, we will be representing a probability distribution as a function in the reproducing kernel Hilbert space, and that function will be the expectation of the section. Okay. So, depending on the kernel, so depending how rich is the feature space corresponding to the kernel, this might be injective. So for instance, so I think second day I mentioned that some kernels are universal in the sense that you can approximate any continuous function. So basically, if the kernel is universal, yeah, this maybe I should say later, but it's okay. So if K is a universal kernel, like the Gaussian kernel, then this transformation is injective. Meaning that if the distributions are different, the representation in the Hilbert space has to be also different. It's not like with the polynomial kernel that I can have two probability distributions that are different, but maybe the moments are the same. But maybe before we keep talking about why these things can be useful and so on, let's have maybe technical result that is also useful, right? Because you might, or at least some of you might be thinking, okay, why is that you can do these sort of things? I mean, this is, I don't know, is this a valid operation to do for any P? I can do these expectations and get an element of H, or in which cases I can define this. So let's do a little result showing that this is well defined with a small regularity condition. This is well defined, and also this result is going to show maybe the main property or one of the main properties of this embedded. Okay, let's see the theorem. So if the kernel satisfies that, if the kernel and some probability distribution satisfies that the expectation of the kernel of the diagonal of the kernel is finite. For instance, if so happens that these quantities are bounded. So this is a slightly stronger condition to this. This is also what we told with Xavi the other day, right? So if the diagonal of the kernel is bounded, or if for that specific probability distribution this expectation is bounded, then that thing there I call P expectation over P of the section is actually an element of H. So it's well defined. And in addition, we have a very nice property. In addition, we have that well, so this embedding is an element of H, so I can pick any function in F, and I can do the inner product of that F with the embedding of P. Right? I can do that. So both functions are in H, right? Right. So then, what do you think we will get with this, right? So now this is going to give us a generalization of the the reproducing property, right? So
if this thing is a section corresponding to one specific x, we know that that will give us the value of f at x, right? Right. So if we do, so the reproducing property was like this, right? This is the of x. That's the reproducing property, right? Now, this thing would be exactly this if the probability distribution is the point mass at x, right? We are generalizing this so that this is going to correspond to general probability distribution, right? Okay, so maybe we can think again in the example with a probability distribution supported in just 2 points, right? The embedding of that probability distribution was the combination of two of these guys, right? So if I put in here that combination of the two guys, I'm going to get a combination of the values of f, right? So in general, what I will get in here is the expectation with respect to P of f. We are going to prove it, but this is basically, at least I guess it's clear for everyone that if the probability distribution is simple in the sense that this combination of point masses, then this is true, right? Because it's just using the linearity of the inner product, right? So if in here I put the combination of sections, I will get the same combination but in images. Okay, so basically in this result, we are going to prove that this happens for any. And I guess it's also clear that this is a nice thing to have, right? So basically now, if we have that, every time we want to compute the expectation of some function, we can just do the inner product between the embedding and the function, right? And that is useful for multiple things. Okay, good. What else? Well, also this, I mean, this might look like a strange thing, but if you think of it like in the case of the polynomial kernel, right? In the case of the polynomial kernel, this is just saying that, well, if I do, so this will be basically the expectations of different moments, right? And this will be a function that is in that Hilbert space. So to be in that Hilbert space, it means that it's also polynomial, right? So this is basically saying that if I want to compute the expectation of a polynomial, I just need to know the expectations of the moments, right? And then the expectation of the polynomial will be just doing the combination of the expectation of the moments. So in that example, it's straightforward. In general, maybe more interesting. Okay, so let's prove this. What is this? Yeah, let's prove this and maybe let's stop here. Okay, so the proof is basically the same type of proof we did 2 days ago when we were talking about the reproducing property and the sections and so on. This is just an extension of those ideas, right? So 2 days ago we present the sections and the reproducing property using the evaluation function, right? So in here, we don't want to get the images of f at some specific point. We want to get expectation. So, and the functional that we are going to consider is a functional that for every p, instead of for every x before. Okay, let's do a notation maybe more suggestive. So I'm going to call this functional expect. and it's going to be a functional for every p. And this functional is going to take functions in H and give us real numbers. It's going to be like the evaluation functional 2 days ago, but now it's going to do expectations. Instead of evaluations in X, it's going to do expectations with respect to P, and this is going to take F and transform it to the expectation of F. So this is a function from the representing Hilbert space into the reals, no problem. And it's going to be linear also, right? Because expectation is always linear. So this is a linear operator. And we are going to show that this is continuous. Right? So 2 days ago, the fact that the evaluation was continuous was either an assumption that we make or maybe a consequence of the fact of being a Hilbert space. Now let's prove that this is continuous. So it's the same definition as before, right? So basically what we have to do is to check that the expect operator at every, or for every P at every F is smaller or equal. So now we have to find a constant that depends only on P, right? And then bound it with the norm in the Hilbert space of F, right? So this is what we want to do. We want to prove this so that this operator is continuous, right? So this is what we want to do. Okay, so let's do it. So the expectation, so this is the absolute value of the expectation with respect to P of f of x, right? And now this expectation is going to be smaller or equal than the expectation for P of the absolute value of f of x. Right. This inequality you can see because of the properties of integrals, or you can see it as a consequence of Jensen inequality because the absolute value is a convex function. Okay, so then and now we just have to bound the absolute value, and this we do as we did before. So this is going to be smaller or equal. The expectation stays the same, and in here in here I forgot the square root. Right, so the absolute value we bounded 2 days ago as the product between the square root of the diagonal at that x times the norm of f, right? I guess you remember we did this a couple of times, right? Yeah, or maybe more than a couple, right? So this appeared multiple times. This type of inequality was used for multiple things, right? And now this thing is this, and this other quantity here is going to be something that depends only on P, not in F, and is going to be a constant because we are assuming this regularity condition, or this other one that is stronger, right? Okay, great. So then we have this. So then this is okay. So that this linear operator is continuous. And then just as we did a couple of days before, since this is a continuous linear operator, we can use Reed's theorem. And then we know that there exists an element in H. How should I call it? Let's call it phi of P. So for every distribution is going to exist an element in H that this operator is the same as doing inner products. With respect to that Right? So that's this theorem. Right? And now the only thing that remains to be proven is that this element in here is exactly the same as the tau p. Right? So using this theorem, we know that there exists an element in H that satisfies this. So the only thing that remains to be proven is that this pi is exactly the tau p I defined before. So let's do this. Where should we do it? So let's do it here. Okay, so let's show that that's the case. So both. I mean, this is an element in. This is an element in H. So let's prove. Let's prove that this exactly that that element in there. So in order to do that, we just evaluate it in any x prime, right? So this is an element in H. So the value at some specific x prime is going to be the inner product between the section and the pi p. So this is again using the reproducing property. If you realize, we are always using the same 3 or 4 properties again and again and again, right? So this guy that we just proved that it exists, if we evaluate it in any point in X, is equal to this, right? And now this thing, what it is, well, we just said, right? So this, if we do the inner product of this pi with any function in the Hilbert space, we get this quantity here. So this is the expectation p. Now the specific function is x prime, is this specific function. Right. Right. And this guy here is our definition of tau p evaluated in be more specific. So we will be doing the expectation of this specific function in x prime, right? So we will be doing the expectation with respect to x. So this will be the thing I defined as tau p evaluated in x prime. I changed the order of x and x prime, but these things are the same because this is symmetrical. Okay, so then pi p is the same as this thing I called tau p before, so we have what we wanted, right? Okay, good. So yeah, so tomorrow basically we will be using this representation of distributions inside the Hilbert space for a couple of applications, like defining distances between distributions and how these distances can be used for the applications. Yeah. Oh, yeah. So, and there was something else I wanted to mention, something very simple about this Kerner embedding that can be also useful to give you the intuition. Okay. So there is a very simple application of these ideas. Right? So a very simple application of these ideas is like, well, so we are representing a probability distribution as a function in the Hilbert space, this type of function here, right? So this is going to be a function in the Hilbert space, but this function would maybe not look like a probability distribution in the sense that this function might take a negative values or whatnot. This is just going to be a general function in that Hilbert space. is not going to integrate to one or anything, right? But if we choose a kernel that, so for instance, if we choose as kernel, let me see if I do it right. So if we define the kernel to be like this, if we define the kernel to be like this, which is basically the Gaussian kernel, but in which I multiply by this constant. Right? So if we use this kernel, which is basically the Gaussian kernel, right, normalized this way, and now we do this mean embedding, what we are going to get in here is going to be also a probability distribution over X. Right. So for instance, if I have, so I mean, this we can define for any probability distribution, right? So if I have, I hope it's not confusing. So if I have now n IID samples, if I have now IID samples from some distribution P, right? If I have n IID samples from some distribution P, I can create the empirical distribution of these n samples. And okay, so I can define the empirical distribution of these n IID samples, right? So this empirical distribution is a distribution that puts probability 1 over n into each one of the samples and probability 0 to the others. Right, so this is the usual empirical distribution. Is going to be an element here. If we represent it in this Hilbert space, what we are going to get is going to be convex combination. So if we embed the empirical distribution into this Hilbert space, we get this expression here, and this expression here is what people call the kernel density estimation. I don't know if you have seen the kernel density estimation before in your life. So basically, okay, let's make a picture, right? So kernel density estimation, if I have some samples, the kernel density estimation basically does a Gaussian for every sample, and then add all of those Gaussians, and the final result is an approximation of the density formed by combining multiple Gaussians. Okay, so this is a very simple application of these ideas. I mean, more than an application, is a different way to see kernel density estimation. So kernel density estimation can be seen as representing the empirical distribution in the reproducing kernel Hilbert space given by the Gaussian kernel. Okay. So this is a very simple application in which we don't do anything. It's just plugging in the empirical distribution and see what is this, what is the embedding of the empirical distribution. Right? So the empirical distribution is an approximation of the actual P. What we are doing with this embedding is finding an approximation of P that is as smooth as the functions in the reproducing kernel Hilbert space. This is. I don't know if with these examples I confuse you more, or I guess for people that is familiar with kernel density estimation, this might be an interesting interpretation. For people that have not seen kernel density estimation, might look a little bit strange, but yeah. Okay. So basically, one very simple application of these ideas is to estimate probability distributions using functions in the reproducing kernel Hilbert spaces, so that all the smoothness properties, of the reproducing kernel Hilbert space are utilized to approximate the distribution. Yeah, question.
Yeah, you say that this is another way to see kernel density estimation. What is the original way to see it?
Well, so the original way to see it is, I guess, like what I was plotting here. Like I have a bunch of samples, and then I'm going to approximate the distribution using combinations of Gaussians or some other function center at this example. And so the usual way to say kernel density estimation is, let's approximate using combinations of kernels. And well, I mean, it's not only like that, right? So you want to make some distance as small as possible, and that can help you to choose what is the right scaling parameter and so on. But yeah. More questions, comments, something else? Okay, so tomorrow basically we will finish the course, seeing few more applications of this kernel mean embedding, and that will be it. So, okay. Let's